team first slides first. Team 1. So these are GE folks, all grouped together. All yours.
Yeah.
I'll click us forward.
All right. I'm Lee. This is Max. This is Christian. This is Mary.
So even if you stand it there, it's okay. We have one more.
All right. All right. So our project was kind of creating a formation around a leader quad rotor. So we're tracking and controlling a formation, and yeah, there we go. There's a picture of a few in a swarm, I would say. Go ahead. And so you guys might have seen it, but this is from the I think the Super Bowl, maybe the Olympics, of quad rotors talking together. And if these quad rotors talk to their neighbors, they need formation control, and it's too much processing power to talk to each one of these individually. So we'll talk to their neighbors and say, what I need to know that I'm around here in this area compared to my neighbors. So we save on, processing power, and so we can scale up in terms of, Quadcopter in terms of that. So lots of applications in terms of, aerial presentations or other types of swarms for the military. And yeah, I think we all points here.
So like Lee was saying, we created one leader quad rotor and 3 followers. So the leader has a program trajectory. We just used a figure 8 that we made previously. And then the 3 followers kind of follow the leader in a time varying formation around it. They don't know the trajectory. And I think that's kind of all this says here. The bottom is just kind of how we went through this. So, we started off modifying the code we had previously from the course to, add 3 more quadcopters. We then created the time varying formations, added a new control function to implement for those followers, and then kind of tuned it up to tune our gains so that it would perform as we wanted. So like we said, all of the quads, so they communicate their actual position and velocity. We're not implementing a range sensor from one follower to another. They can communicate their actual states. And the leader can always communicate with every follower. So there's a range sensor, so the followers can only communicate with the followers in a range, but they can always talk to the leader. And then we assume gravity is the only external force, so we're ignoring wind and all these other things that make it more complicated.
All right, so here's some of kind of like the diagram of how we did it. This follower control and dynamics block is what you're used to when we did all our homework, and what we implemented was the framework around this. So we call this the outer loop and the leader quad dynamics trajectory, because that would be the inner loop, and it's kind of hidden in here. So like Max said, if we're in range, we take that into account of a difference of velocities and positions, and we have some gain influences here. And so we take in range of followers and the leader, and we use the inverse mapping to get our commanded values here.
So once we implemented what Lee just presented, we kind of went through some demos. So the first was a simple triangle formation. So this was each quad rotor follower was a set distance away from the leader. Again, like Max said, they had no knowledge of the trajectory of the leader, so they're moving based on the distance that they are calculating in the function Lee just explained. So for this demo, it was literally just 3 followers in the 3 locations that were set, and their goal was to hold the same location away from the leader the whole time. So as you can see, like when it starts off, it's still trying to like kind of stabilize. Even the leader is stabilizing with the way we had set up our controls, so all the followers are following at the leader as it's getting used to its trajectory and moving forward. On the next one that we did a time varying formation. So if you watch, the followers will change their triangle formation around the leader. So they kind of start off in like a horizontal triangle, move forward, and then make a vertical triangle. So again, like when this is happening, each follower location from the leader is being used to control it. So it's being told at a certain point to go in a certain formation, and then based on the time, it was changing formations. As you can see in the bottom, we saw the number of neighbors per quad rotor follower. Oh, this is on the next one. It doesn't matter. But this plot on all the slides that we're showing is kind of just showing which neighbors it's talking to. For the majority of these, in order to keep them stabilized, we had to have the followers talk to the leader if it gets lost. Right there. If it gets lost during the process. But we did do some experiments later on where we took that ability away from the followers to see what would happen if it had no instructions on where to go. So now you can go to the sphere.
Sorry, this like moves screens.
Oh, it's all good. So this is our first sphere rotating demonstration. So for this, we had the 3 followers going in a sphere location around the leader. So I know it's kind of tricky to see in the 3D, but you can kind of tell here, we had one going around bird's eye view down, one going around vertically, and then one kind of going diagonally. So each axis had a follower that was circling the leader. I think it's all on this one. So on the next slide, we did the moving rotating sphere formation. So this is where we moved our leader and then had the quad rotors continue to circle it. This was the one that took a little bit more tuning and gain work in order to make it work, because if it was too sensitive, then they would just fly off the rails. If it wasn't moving fast enough, then it would also fly off the rails because it would lose its position. So I know it kind of looks like a jumbled mess of spaghetti, but this is the 3 followers doing the circle rotation around the leader in every direction. I could go next slide. So I talked a little bit about range changes. So in these 3 simulations, the leader is always visible to the followers. So this means when it's 0 here, it can still communicate to the leader, and that is how we ensure that it didn't kind of fly off the rails. But we all know in the real world that's not always possible, right? So in the real world, if we had this situation where the range threshold was smaller, then the followers would have no idea where the leader is in addition to all the other neighbors. So we ran another one on the next slide that sent the followers to the origin point if it lost contact with all the neighbors. So for this one, you can see that in the smaller range, it was very unstable. And although the leaders, the followers were trying to return to the origin point to maintain their distance away from the leader, our path that we were having at circle was larger than what this range allowed. So like our circles around the leader were a little bit over 5 like meters or 5 distance away. So when we tried to do that 2.5 range threshold, the quad rotors kind of just flew off the handles. But it did work for the range threshold of 5.5 and 7.5, just showing that kind of obviously the range needs to be, at least being able to talk to each other as it's moving through its trajectories. It needs to be able to have a neighbor in order to continue behaving as intended.
So, like MT's talking about, theoretically, using this type of a control, you could control any type of formation with any number of quad rotors. But like she mentioned in the last one, some of the formations require different gains in order to control them smoothly. So it brings up the point, do you trade off between a slow and accurate convergence or a quick and less accurate convergence to the new formation if you're going to do time varying? And also, if you do want to go to a new formation, if it's significantly different than the previous formation you're in, you might need to retune the gains, which brings up issues if you're trying to do like the Intel Swarm, where they're making like the Pepsi logo or a snowboarder going down the slope. So how do you retune those gains on the fly like that? So that's one of the current limitations of what we implemented. The other limitation is, like MT mentioned, currently the method fails if the follower does not have any other of the quads in range. It can't talk to any of the quads. So some of the solutions to this could be that they can always talk to the leader, like we mentioned, or they return to a known waypoint. And she showed a situation where returning to the known waypoint of the origin became unstable. you could reconfigure that control system on that particular drone that if it goes out of range, it separates that portion of the control. It doesn't do the formation control anymore. It has a separate control. It'll take it back to a waypoint. So future capabilities that we thought of that could implement into this to make it a little bit more complex, a little bit more capable. You could have adaptive gain control, like I was mentioning about changing the formation and changing your gains on the fly. You could implement an EKF into this. You could have range sensor based. The math was getting pretty hairy when we were doing it, so we decided to go with that they can just communicate their states directly to each other, which is what we mean by the RF comms based. Collision avoidance, so right now they can fly right through each other, no problem. Obviously that's not realistic, so you could implement some collision avoidance, and then theoretically scale it up to any number of quads that you want to. So I think that's it, if anybody has any questions.
Okay. Questions?
One question I have is I mean, you have a parallel implementation of several quad rotors. So was this completely, I mean, was it a synchronous implementation, or there is a possibility for asynchronous communication between the as they move in formation? And second question is, of course, the scalability issue. I think you put it as a part of the future work, correct? At what point it becomes like computationally complex to implement in the current software platform that you have?
Yeah, so for the first question, we wrote a function, so it was doing it not synchronously. Well, it was one after another, right? So it was like synchronously in the same loop, but it was happening one after another, right? So in order of followers. So I think, yeah, that could be, like you said, an issue if there was any like vast changes, and kind of shows when it was being unstable in some of those range information, it kind of just flew off the handle because it was changing too fast. Your second question, I don't know if one of you guys feel like you could answer it.
I don't know too much about the limitations of what
Yeah. So right now we use like 4 of them, right? So did you try like 5, 6? Did you try to increase that number? But I mean, already this is a great project because implementing movement of 4 quad rotors in parallel in MATLAB simulation is a great milestone that you have achieved.
Yeah, I don't think we tried to implement more than 4.
Yeah, we started at 1, so we worked our way up to 4.
I also don't think it would be a problem. I think since we don't have any collision detection logic or anything like that, it would work fine. But like obviously implemented in real life, they would crash into each other. But
Consider that future work.
Yeah.
So what was the answer for synchronous? Like, as they were communicating all the time at the same time?
Yeah, it's basically like at every time step, they all calculate where they are relative to the other ones. Mm-hmm. And then they calculate their commanded values.
So did everybody were talking to leaders, or only one follower was talking to leader, like, or it was based on
They're all
range?
talking.
Yeah, so
one of the slides, it was
we took that out.
We took it both. We did it both ways.
Yeah. So we
did
it
both ways. That as long as the graph is connected and at least one follower is talking to leader, it should work, right?
Yeah, exactly. Yeah.
Okay. Other questions on online, folks? Let's Dr. Karega.
So what would you have done differently to restart this project?
Definitely some code cleanup work. We were running into some random issues where we were like, the way we had hard coded things in when we initially were trying to make it work, left like some artifacts to like divide by 0 was like one issue where one of our functions, the way we wrote it, it didn't make sense. So then it just kept trying to divide by 0. I think the other thing would probably be just like,
make it a little more general.
Yeah, less copy paste, because we would do a lot for one and then just be like, okay, now do it again for the next quad rotor. So more functions.
I also would say the adaptive gain, there was a lot of, we ran into like, I would make a formation, it would work fine, and then somebody else would make a different formation with the same gain values, and then that wouldn't work. So if we made it smart about how it calculated those, that would have been nice.
That's where the learning part has to. adapting to the new number of vehicles or environment? Or,
Yeah.
So Krishna, do you have insight? Like, how do people solve this problem of with different vehicles, different environments? Does gain needs to be changed in your opinion, or?
The gain, you mean to say?
Yeah, the gains, yeah. Controller gains that they were using.
Yeah. That is new to me too. Controllers. Yeah, I worked on the swarming aspects, but not low-level controllers.
No, the KP and KV are the formation controllers actually. So they
Right.
are that they need different KP and KV if there is a different formation or a different trajectory.
Oh, I see.
Yeah.
I mean, according to me, the KPKV setting of that affects the response in terms of how quickly they get into that distance criterion between them. So it should be independent of like different formation structures.
What is this N?
And again, if we can you can actually model it as approximate it as a second order system, and the second order system guides drives the tuning of those gains.
It is actually a second order system.
Right.
Yeah, anyways, yeah. So other questions from the class here? Participate, folks. There are points for participating also. Yeah, go for it. You were doing this. Anybody? Melody?
So just Rajni, just for, while I'm scoring them, I'm doing it on an independent sheet so that I'm not biased by what Prashant puts.
I realize that people can be biased.
And then in the end, I will upload the grades.
Sure. Thank you. Okay.
All right, thanks.
Okay, thank you.
Thank you.
That was so bad, huh? Okay. So we have a second team now. It's UAV landing on ship by Thomas and Dylan and Stephen. Is this the latest one, or do you have another presentation? So this is. Okay, just come off the title. You'll come here or? Yeah, sure.
Yeah, it sheared off all of the design. That's
the whole format just that's weird.
That's Microsoft still working on it, I think.
Yep. Okay.
Yeah.
Download from maybe Windows to Mac, I don't know.
Yeah. All right. Fair enough. We'll run with it then. But yeah, I don't know why.
We will not get any point for design.
Fair enough. All right. Well, we designed just a UAV using our quad rotor landing on a ship. Of course, just our group, myself, Thomas, Dylan, and Steven. Our objective slide is effectively telling us what our entire goal was as per assigned and what we were turning in, that creating a dynamic model that we would then be producing as this landing on a ship in multiple different configurations as shown above. And then output video, state plots, error plots, and trajectories showing how successful or unsuccessful any attempt was. The background on this topic is we went through multiple different papers where we were discussing what people did before us, how we want to take what they did and improve on, or what we want to focus on differently. For most of the projects we saw, again, we only went through about 3 or 4 different research papers. They focused more on the air effects and the things that were affecting the UAV directly rather than the ship, or the ship effects about even surf, or the ship turning or ship going in certain different lines or trajectories or courses. So that was kind of what we then want to boil on and then move on through ours. The different applications of a UAV landing on a ship could be anything from search and rescue, especially on aircraft carriers and environments where we can't have boots on the ground, for both military and civilian applications. Surveillance is another big issue that's both been contentious in media as well. We also then do validation of GIS data, especially for environments where not many people live there, or it's not really all right, there are not roads, houses, cities, or anything. And if you need to be able to take data of these vast areas, it's much easier to take drones than to walk around and do it by hand, which is another huge issue that even throughout the Western United States that we work on.
Okay, as Thomas touched upon, most of the papers were focusing on the effects on the drones themselves, weather conditions, gusts. We chose to focus more on the ship movement. So we did 3 different tests where a ship is moving in just a straight line, where it's going in a circular pattern, or when the ship is going moving in a straight line, but it has some disturbances, so that would be like surf for the naval ship.
Okay, this is yeah, no,
This is not the right
this is not the right slide.
Did you turn in the wrong one?
Did I turn in the right one? Okay, yeah, yeah, this is.
Do you want to send again? Or
Yeah,
you
sure,
want
I'll
to-
try to send it again. Yeah, it's almost like it's been.
It's weird because he saved the PowerPoint. I watched him save it.
Yeah, yeah.
And then,
Was it on Teams?
yeah, it was just
Sorry, folks. Technical difficulties.
This is what happens when you turn something in at midnight.
Yeah, you can email. Or so who submitted? Thomas, you?
Yeah.
Yeah.
See if the design holds here.
that's weird.
It's really strange. Maybe he just turned in the wrong version.
Yeah, so that
Yeah.
might be thing. Does it have HDMI?
Yeah, I mean, yeah, this was supposed to look like with
Okay.
all that design, but.
Did you send me a link?
Yeah, I just sent you an email with the PowerPoint attached. Since yeah, I have no idea how that even got it into a turn-in box.
That one should have been overwritten
Yeah.
when you saved it.
Seems like somebody's cooking. Did we mute these guys? Let's see. Okay, guys. So I think it should be good now.
Yeah, sorry about that.
That is crazy. Okay, yeah, I will correct that submission as well after this.
There we go.
Alrighty.
It's a bit better.
We'll just quickly just do over that then, since that was quite weird. But yeah, again, you would be landing on a ship. Overarching objective, now that there's actually additional text here, again, has to deal with how we moved in straight lines or differing configurations, especially when turning, that we found that there could be definitely adverse conditions when you're trying to land on a ship that is not moving in a course that you're actively expecting or in a rough sea. Again, applications such as validating GIS data or surveillance or object shipping, especially when we all heard about the Amazon drone service a couple of years ago, that's still kind of been very much in development. And now with anything from wildfires to being able to locate missing people and the applications are largely endless in this regard.
So we still have the same approach. We wanted to look more at the ship movement and tracking different ship movements, so straight line, and a turning circular motion, or just where there's disturbances, which would represent surf. Here are the equations we use, which are the same ones we've been using for the whole year with our quadcopter, and then just the standard northeast, and then positive down.
And so now we move on to the actual controller itself. And so our design is basically two different LQR controllers that we switch back and forth based on the state of the quad rotor itself and its relation to its target destination, in this case being the ship that it's trying to land on. And so when it's further away, there's one LQR controller where it holds at that altitude and it moves over in the northeast direction so that it can hover over its landing target. Once it realizes that it's within that version and that state, it switches over to the other LQR controller where it will slowly descend down to its target, hopefully, safely. And if it then moves back out of that situation for whatever reason, it can't keep in track, it will hold that altitude. So it won't keep going back down.
And then due to some of the issues with having to put a embedded video of this length in, we're just pulling that up if that wants to. Yeah. I thought it wanted to do it. It brought me out of the slide deck and then did not open the video.
We're not Mac users.
Sadly not.
So did it come here?
Yep, there it is.
Okay, so let's start it here.
And then
Maybe I'll just sit here. Okay.
yeah, is there a way to bring it back up on that?
Yeah, so they can see it on the.
Okay.
Yeah.
Display. Preferences. Arrangement. Mirror displays.
There.
Okay, so now it should be.
There.
Yeah, okay. So here you see our first experiment, which is just the boat moving in a straight line and the quad rotor quickly coming down to assess it. You can see there's a couple points there where it holds its altitude again because it can't quite keep up, but eventually does make contact.
And then
We go to the PowerPoint.
yep.
There, that's okay.
Oh, it just swaps it right back. Okay.
Yeah, and then we have state plots. These are our phi, theta, and psi commanded. And in orange and in blue is what we actually achieve. So we're quoting pretty close. Here's our error plots for PN, PE, and PD. So we start about 10 meters in altitude, 3 meters away in east, 6 meters away in north. Swap that, and then you can see us coming back. And we have a bit of steady state error in the east direction. That's just one of the issues we ran into.
Circular path.
Still doing the same thing?
Yep. It wanted to bring it up again, and it's.
We should skip the video for the third one, probably.
Yeah. I see. I didn't realize that every time I was going to enter present, it would redo all of your settings over
Yeah, I
again.
don't know why would it do that, right?
Yeah. I'm actually surprised the computer lets it force it on that like that.
Still no. As soon as we go to PowerPoint, I think it's doing that. So
Okay. Then it drops in Safari.
where's this?
Should be right there. Yeah, I think right there. Doesn't look like it wants to load it. That's the old presentation, yeah. Y'all check that, because I have no idea. I deleted that. Yeah.
Really strange.
Because it brought in the exact copy over from Google Slides.
Yeah, maybe it was just.
Maybe it's saved in a temp file somewhere when I went to go turn it in,
Yeah,
and that's
saved
just
it.
what it thought it was.
Yeah, save the temp file and the temp file uploaded. That's weird.
There we are.
Why would that change?
I have no idea why. The link, the hot link is taken to an untitled page, but when you copy and paste it, it's fine.
Okay. Maybe don't.
Yeah.
Present. Don't go into present mode.
Will not go full screen. Gotcha. But yeah. So.
And then this is our second case with the boat moving in a circular pattern, as you can see, and then the drone comes down and then kind of moves with a little bit. It sits there at a few times, it sits at like the same altitude until it can reach it, and then they eventually join together. And then
Gotcha.
Or I can just skip the third video.
Yeah.
And then
Yeah.
and then same thing as before. We have our state plots, then our error plots.
With some additional slight error as it
Yeah.
comes out. However, it still did eventually land, just due to the way the boat was moving. It was forcing the quadcopter to move with it throughout it.
And then,
Do you want to show it or skip it?
You can run it.
Yeah, just-
Just copy and paste.
No.
Control command, control C thing, not control but
Command. Gotcha.
Apple.
command.
Command V. So for this, the disturbances were greatly exaggerated. It's the only way we could get it to actually show up on data, because otherwise the adjustments would be far too smooth for our graphs to kind of recognize as a potential error. Again, it wouldn't normally be like this. However, the disturbances are moving in all directions to simulate, I guess, supposedly worst case scenario uneven surf. Again, this was more manipulation of the way the quadcopter would be reading what exactly the ship is doing. Back to this. If it wants to. All right. Again, with state plots, nothing too crazy here. It actually reacted extremely well to it. However, when we go look at our error plots, we can definitely see at points where the quadcopter would all of a sudden be knocked back off course and then immediately adjusting to come back on and be able to land. Again, if we were to make larger waves or push it far out, you'd be able to see more of a potential sine wave. Although that's not totally correct, it would show how it's compensating with larger waves or any sort of dips or dives throughout these waves.
So then here's our 3 different trajectories. So obviously the blue represents how the ship's moving, and then the black line shows how the UAV is coming down and then eventually meeting up with the ship and then staying with the ship.
Yeah. Excellent. That's about all there is to that.
Future research we would move on from this is looking at not only the adverse sea conditions, but wind conditions adding on to it. Also additional drones or some sort of queue system for if we need multiple drones landing on a ship, but we can only fit one at a time to create some sort of holding pattern. Multiple ships as well if we want to move, say, one single suspended load from ship A to ship B, and then you can see as we can continuously compound this with additional drones and or ships. And finally, just more complex ships courses. This one we were more showing a proof of concept of how exactly we can get things to work, and then having a drone come down and land on it, and one of the errors that we were shown earlier is that if we were to say move a drone too far out or have the distance of the ship moving too fast, we could run into, again, motion equations on the UAV either never catching up or going to such crazy overcorrect that it would throw itself off of the trajectory completely. And then, again, sources for our various research papers and questions.
Can we go back to the error plot?
Which plot?
The error plot, 16.
Yes.
All right, so I see a negative error for PN. Obviously, we don't want that when we're landing on a ship.
Yes.
Well, that's, well, PN, like north, east, and down.
Or, excuse me. Never mind.
Yeah, it's all good. Yeah.
All right, excuse me.
Yeah, we did have.
Yes. Although we did have to actually go about correcting that while we were fixing it, because we did realize that we don't want to slam through a ship.
Yeah, we did have to adjust gains a couple times because it would fall too fast.
So is this the error between the quad rotor and then like landing on the ship, so the ship location?
Yes.
Ship location, yeah.
So when you talked about you had to do a lot of gain work, right, to make it not slam through the water. Is that
Yes.
kind of where your east error came from, or is that still on the boat? I guess with that error.
Yes, it is.
Yeah.
So it's highly exaggerated here, but it would be as if you're landing a foot off or a meter off from where you're supposed to be, and on a big landing pad. That wouldn't be a huge issue.
Yeah.
However, we did notice that, and he can talk more on this, but as we were trying to tune, we could start bringing it much closer, but we'd be sacrificing the overall accuracy and the time it takes to actually converge, which we thought a small amount of error that was consistent would be more acceptable than just going for chaos if it meant everything eventually converging.
Yeah.
Other questions?
So when you consider the simulation of the boat, do you just consider? Do you consider the dynamic model of the boat, or just you connect directly feed some like position and velocity to the animation of the boat?
We just feed a direct trajectory to the boat itself. No
I
actual.
see. So right now you're considering the dynamic model for the landing like aircraft, correct?
Yeah.
Yes.
Yeah. Correct.
I see. And how many states do you consider? Is it a 12-state model?
Yes. Yeah.
Okay. Thank you.
Any other questions?
So what happens when it lands? Does it?
Yeah. When it lands, it just stays there at that spot. We didn't program like an end cutoff state.
Do you also see the same similar east error in other cases?
It was in all.
How long is your boat?
The actual boat in the animation is only 1 meter by 1 meter.
Mm-hmm.
But that's just for the sake of animation.
So in the circular one, it's slightly more hard to be able to tell, but there is some error on both sides just due to the way it was moving. However, again, we're having this be highly exaggerated.
North, east, down are the inertial coordinates, or?
Yeah.
Yes.
So so I think putting errors in terms of body frame of the boat would have made more sense.
Yeah.
So where are you with respect to the body of the boat, like in X and Y direction? It would have made more sense whether the quadcopter is actually on the boat or not. Right now, it's confusing that.
I see what you mean. Yeah, it was definitely a consideration of trying to be able to show multiple things with one.
Definitely.
Other questions?
What's the x-axis? Is it times or is it just the samples?
Just a sample
Samples.
time. Yeah.
Any other questions? Okay, give them. Thank you, folks. Hopefully, no more video links. So we have project number 3. Team 3, I think, you guys are going online link? You have a Google link, right? So, what was that link? Let's see.
and then I turned it and put it back, and then I had to like manually.
So what is your team?
Shama? Shine.
This one.
Both of them jump around these two. Start from the beginning.
What was that?
Yeah. We can,
So, okay.
There are animations.
So yeah, okay.
All right, so good afternoon, everyone. Our project is about estimation and landing of UAV on a moving platform by using different, like multiple landmarks and to get the position of the quadcopter. And I'm Hong Chi Kwon.
All
right. So before we go into our project, I'm probably going to briefly talk about why is UAV so important nowadays. So for the technology, UAV has been used in for scientists to collect and gather data from different like air, sea, or like ground. So we don't have to send like several teams to the place, and we can gather the data like easily and correctly. So for commercial use, we have used in like inspections and like agriculture and lots of like aero photographic. And for military, we have like surveillance and like target attacks and lots of like UAVs, like compact UAVs. And industrial, we have like lots of like security and some like emergency call. We can use a UAV to do it. And for the market size, in past year, 2020, UAV has been like 20 billion prices in the market, and military takes like 65%, and commercial do like 22%, and for industry it's like just briefly above like 10%. So for our problem statement.
So we all know that we used static landmarks for our project in our class, and well, it gave us pretty good results somewhat. But if the drone or quadcopter moves out of the range of the landmarks, it won't be able to sense it, and it might be lost, right? So what if we consider a moving landmark, which is always around the quadcopter, so that it can take data out of that quadcopter and estimate its position? That's one of the concepts that we considered. And the other thing is, yeah, in most of the applications, probably the drone might want to land on the moving platform, like in case of logistics, right? There are a lot, you need to get some packages out of some high place and bring it out onto a robot, which can transport it to some place. So that we can do using this concept of landing the quadcopter on top of the moving platform. So that's what we are considering as our problem statement.
So as we mentioned in class, we know about the PID controller. It's a control loop mechanism, and it's usually for linear systems. And for LQR controllers, it's a closed loop, and we usually use it for nonlinear like models rather than the PID do's. So that's why we choose LQR for our code and to reducing the distance error for like our project.
talking about the extended Kalman filter. So as you mentioned, that our system is non-linear, and in non-linear case, extended Kalman filter comes into effect. We have already studied how it works, where it considers the distance error as well as the covariance matrix to update the state of the system based on the previous states, and also considering the updates from the measurements from the sensors. So that's what this is all about. We have already discussed it, so just moving on further. Yeah, the same thing. We can consider the gain and covariance equations and reduce the dependence on the estimated value of the state with extended Kalman filter. So as I said, to achieve a better estimate, we can either increase number of landmarks, but it can also be, can also cause hindrance because of a lot of landmarks coming into effect and increasing uncertainty in the measurements. So that could also be not beneficial for us, and we can also improve the sensing range, but it would be highly costly. The last thing we are considering here is a moving landmark nearby quad, so that the estimate is better. Now, to get on top of a moving landmark, it can directly be done using PID controller or LQR controller to reduce the error towards the moving landmark and going towards landmark so that it can land on top of it. But sometimes it's not ideal, because you can there could be a lot of obstacles in between, which we might want to maneuver around. So there is where path planning and tracking comes into effect. And there are a lot of methods of path planning, but because of time limit and lack of understanding, we rather chose to go with a control strategy. A simple control strategy of 3 steps, where the quadcopter will move towards we are just considering a linear motion of platform over here for our ease. So the quadcopter will first move towards the plane along which the linear motion of platform is occurring, and then it will try to follow the plane, and as soon as it is in or around on top of the platform, it will gradually drop onto the the platform. That would result in a safer landing. However, because of some coding difficulty with these 3 steps, we finally decided to go with a direct landing with control gain. So for our case, we consider the simple kinematic model of the moving platform, like this one. We have already discussed about it, and the equations of motion are quite similar to what we did. These are the equations, 12-state model. We consider these equations for our case, and these are the results. Rather than looking into these results over here, let me open. Okay, I don't know. Teams. Okay. I think this will be give us better results. So over here, as you can see, it gradually moves on towards the actual targeted moving platform with time, and you can see that the error estimates. This is the previous was actually the true state that it needed to follow. What is it? This one. This one is the true state. I'll show you in the video itself which one is the true one and the which one is the estimated one. This one is the true one, and these are the estimated ones. So it closely follows the dynamic motion of moving platform. And as you can see, it somewhat goes outside the covariance level as well, as you can see over here at times, because the estimate for a moving platform with error, for the quadcopter estimation, it can come in be a little bit difficult with a moving target, which we don't have any idea about.
So what was your assumption like? What was your prediction model for velocity?
Velocity of?
Like you have velocity as a state that you're estimating, right? How were you predicting it? What was the assumptions that you made?
So basically, we are assuming that a target, I mean, the motion, the trajectory,
constant velocity.
the trajectory of the platform itself is a target trajectory.
Yes.
So that's what we are considering. So the starting position could be away from the.
No, I'm talking about the states that you're estimating, right? You showed a velocity plot. What was the model for that? Like,
the estimation one, the 7-state one that we use in our class.
So that estimate is for the quadrotors velocity.
Yeah.
Okay.
So here is the video that we have right now. So if there is a true trajectory over here, and this is actually a true motion of the quadcopter from our model, but the one which is transparent over here, I have actually bolded out that one over here in the presentation. So see, doesn't actually, the yaw angle is not actually following quite well because we are not controlling the yaw, rather we are just controlling the position and the velocity with our model.
You would have kept yaw equals to 0.
I did, but in the end, it wasn't actually following it. I don't know what the issue was with that. But we could have cut it off right when it landed it, but that cutoff is not yet in our code. So that's the result what we had. And commenting on our method, so as we said, we try to increase the number of landmarks to improve the efficiency of estimation, but it didn't quite work out. And also increasing the distance from the platform, the altitude from the platform resulted in a very incorrect result. So as you see, as I have mentioned over here in the conclusion, the results were not as expected. So it could be because we were directly trying to go towards the moving platform rather than following a good trajectory that we could have developed using more predictive control or probably path planning methods. So LQR may not be as suitable for the case. And yeah, estimation of part position of landing purposes led to loss of connection with landmarks. So when it was at higher altitude, there was loss of connection with the landmarks, and it wasn't able to communicate with those landmarks so that it could land on top of the moving platform. And yeah, we tried to use the 3-step model, but it proved to be difficult by coding. Yeah, that's it. These are the references. Any questions?
Questions online? Wouldn't it have been better to use relative equations of motion rather than like where will you get these landmarks from? Like I'm just being a devil's advocate here, right? So land 3, land 2.
Also,
do you know the position of these landmarks?
Yeah, we are assuming that we know the position.
Yeah, that's what I'm saying. Like what you could have done is everything could have, like all those landmarks could be on the boat.
Okay.
And then you can define them in boat's reference frame. And then estimate position of quadrotor either in boat's reference frame or estimate boat's position in quadrotor's reference frame would have been more. The states, the choice of your states, I'm saying, would have been much better, more practical.
Okay. So right now, I'm assuming that states are in inertial frames.
Yeah, that's right. I'm saying, like, if I'm really landing, you don't care where you are in inertial frame, right? So.
Okay.
Are you also assuming your ship's trajectory?
Yeah, we are considering that the ship trajectory is the target trajectory for the quadcopter.
The quadcopter knows the trajectory of
the ship. Yeah.
So yeah, a lot of assumptions which in practical world will give you a lot of problems.
Oh shit.
Sure, go for it. Krishna, are you asking something?
Yeah, no, yeah, sure. I just had a few questions. Like, I think landing of a quadrotor, one of the main challenges is any wind disturbances. And currently use a LQR, correct?
And we have a little bit of disturbances as well.
You did use disturbances. I see. I see. And then it's a moving boat. Did you try? I mean, do any tests where you are varying the speed of the boat, or it is just you just consider one speed of the moving boat?
We actually considered a case of circular trajectory, and it somewhat did well as well. Let me try to do that.
Oh, you can run it in real time, the simulation?
Using some fancy Google Colab tool. And they have been playing off.
Nice.
I don't know. Oh, sorry. It's connecting.
So this time we did not use MATLAB, Krishna. Everything was Python.
Oh, okay. That's good to know.
MATLAB.
Oh, even all the previous projects were in Python?
Previous ones, yes.
Oh, great. Nice.
And found this Google Colab thing pretty, so you don't need any, so it's just a browser based.
I see. I see.
You can share and, you know.
I think this
like
is
that.
something that Prashant also used in his course.
Yeah, see. So there is the circular trajectory.
Oh, okay. And what are the what's the use of those balls? Are those the landmarks like the blue, orange? Those, what are they?
These are the landmarks. Right now, I'm considering they are in a random position. I could also consider.
And what's their purpose?
So that the sensor on board the quadcopter can sense the landmarks.
Localization. Okay.
Localization.
Yeah,
so basically, they are assuming that they know the landmark positions, and based on that, they localize the.
Localize. I see. Some kind of a beacon localization, right? Beacon type.
Of the landmarks are random. I have also a circular arrangement, but I don't know. Circular arrangement isn't that good.
That's another optimization.
So which means in your simulation, you're not, I mean, you're using the localization obtained from the landmarks in your control, is it? Rather than assuming exact position.
Yeah, we are actually giving them some error in the position itself and using EF to estimate it.
I see.
Controller uses estimated states.
Yeah.
Okay. That's good. Yeah, working controller and estimation together is always there. So you definitely will get some points there.
Yeah, that's pretty challenging. So do you have, how well were your estimates? Was it your controller that's having a hard time or your actual estimates?
So as you can see over here, the dotted lines are the estimated ones, except for the yaw angle, which in the end doesn't actually remain constant. The other thing, I mean, it almost follows the trajectory that was estimated, found out using the model. And we added some error to that trajectory so that we estimated it using the landmarks. So the dotted line is the estimated trajectory.
Have you guys learned to run an observability analysis? Was it observable?
We didn't do the observable analysis, so we can't exactly say.
Are all the landmarks visible all the time?
No.
Any other questions before we switch?
And that was ranged at landmarks, correct?
Excuse me?
What
measurement? It was range, right?
Yeah, range, yes.
Okay.
Range measurements. Keep slide.
Seems like you guys are popular.
Yeah.
The slide where you were explaining about the physics, I think it's what before this.
Estimates? I don't know. I was actually explaining the estimates using the Google Colab only. rather than presentation. Do you want to? I mean, I can move on to the code. This one. Let me try to come out of the slides. Okay.
Here we said something like the gain and covariance equations have reduced dependence on estimated trajectories. So what does that mean?
Gain and covariance. I think I made a mistake over here. So I was actually trying to say that the gain and covariance equations help to estimate.
Okay, folks, thank you. So we'll do team 4. So team 4 is okay.
All right, so our project was using an EKF to localize the position of a raw spot on Jasmine resin, and yeah, very cool. That one, okay. So the problem description right now is that we're trying to estimate the position and the heading using ground hardware, using a ROS Pro 2 robot, and a decawave ultra-wideband sensor, which is just a shortwave radio band to tell us how far away the raw spot is from a certain landmark. And so right here we have, this is actually using a real robot, real life data that we got from one of the TAs who ran a simulation in a little environment with 3 landmarks around. And then the raw spot takes a little trajectory, and we're supposed to predict the position via localization. So the approach we took was to design an EKF that uses data from a ROS bag file. So what we did was we took the real life data and then we can simulate it inside ROS using the bag files, so we can continually test our EKF to make sure it works. So for the states of this problem, it's pretty simple. As it's on a flat plane, we only have to worry about the X, Y, and then the phi angle of the robot. And the initial values for its initial position for the EKF is set to match the initial data for the true states of the robot, just for simplicity's sake.
So for EKF, the first step was to do our prediction step. So we knew the linear velocity, which is v, and then the angular velocity, which is omega of the robot. So multiplying these by the change in time between each step, we could estimate the predicted state at the next step, which is the x of k given k minus 1 function. And then that will be our predicted state, which will get set through the entire process. And then after that, we then calculate the predicted covariance as well in this prediction step using the equation, so you can see with f and q to get the value of p given k minus 1. Which is then pushed into our update step. So for our update step, we use the range equation in order to determine h, which uses the distance of the state minus the distance of the known landmark at each point. And then taking the Jacobian, we get capital H, which is used in the later equations. So these are the full equations that we used later on. So our measurement residual is the true state minus the predicted state. The residual covariance is calculated using the H, and then the P was calculated from the estimated state, and then R is a gain matrix we chose. The Kalman gain uses these values, and then we plug that in to get our updated state estimate from this update step as well as the predicted step.
So we can see here our EKF versus the true results. You can see the blue dots are the true location. So these were measured from the marker data that was on the bot, and then the orange data points are the points that were given for our EKF result here. So you can see that it does track pretty well. There's a couple times that it doesn't track quite exactly, but we will get into why that is. We have discovered the issue there, and it has to do with the measurements from the landmarks. So as you can see here, it does end very, very close to where the true bot is actually at. You can also see the approximate gains for our matrix there. So getting into why it was slightly off here, you can see that these are the measurement plots. So green here represents what we think the true measurement was. So we took the marker data and we cast it to each of the locations and found what the range measurement should be based off of the true data. Then the blue points here are what we were given as our range measurements, and then the red is what our EKF range measurements would have been. So you can see here landmark 1, 2, 3. So we did not run, we only used 2 of our landmarks for that last result that you just saw there, because for landmark 1, we can see that the true green line and the blue line are not very well aligned at all. So we were having issues with the range measurements. We think maybe perhaps the landmark was bumped and we were not given the quite true position of where the landmark was, or something like that. So we elected to just not use landmark 1 because the results were just much better without it. And then also there, discussing the filtering of the data here. So like I said, we did have a couple issues, bumps in the last simulation here around the 40-second mark here, or the 8:20 here. You can see how it bumps out a little bit and then has to recorrect itself. And then at 40, you're going to see it again, or 48 about, you're going to see it again here. Real soon, it'll bump right there. And then it corrects itself. So those come around. You can see here we have a little bit of jump here in the 40, 48, and 60. So every time it got really close or really far away from a marker, it had a little bit of inaccuracy here. And we can actually see this in the unfiltered data that we had to take. And you can see that around those points, we had not great data, you could say. So we had to filter that out. And because our filtering methods aren't perfect, we did have a little bit of jumpiness in our overall final result.
Yeah, so that was kind of a preview of the following challenges faced. The first one was learning how to use an interface with ROS software. We had to actually create a virtual machine to run Ubuntu on, to run ROS, and it was quite a hassle, but we managed to figure it out. And as Dean just said, probably the biggest setback was for the not realizing that our data had to be filtered before it went into the EKF. This causes a lot of headaches because we were trying to basically tweak our EKF because we thought that was what's wrong with it, and so we realized that to look at the measurements that we were getting in, and we realized that we saw all those really huge sharp peaks and everything. So probably the biggest challenge for this one was to pre-filter the data in, as our main range measurements had way too many outliers that really threw off our EKF, even though the EKF was the functioning part. Yeah, and then another thing too is that because of the there is a little offset between the timing of the true and then what the raw spot was basically taking in, so that slowly over time we'd see our EKF kind of like fall behind in the prediction, just because of how we were calculating the data. So we tried to correct that by the averaging out the time distance between each measurements, and then we can account for that way. But it was still a little imperfect, but then in that simulation, but overall we managed to get a reasonable prediction for our EKF. And then landmark 1 was also identifying that was kind of a iffy measurement, was definitely very helpful too. So yeah, we learned that basically using real life data is very difficult and it requires a lot of filtering before, which is really good to know. So any questions? Yes.
Do you have pictures of the setup or?
So a lot of the setup was done by Rohit. So we didn't actually take any pictures while we were there on the first day, and we never got to go back again.
Do you have some pictures?
I have one.
Okay.
Okay. Yeah.
So
Sure.
yeah.
So one question I have is like you did this in ROS. So did you have you didn't put any simulations that involved like a physically simulated robot like moving around that yeah.
Oh, it was all using the ROS real measurement bag file stuff.
Okay.
Yeah, so they had a similar assignment for Quadcopter where they were estimating simulated data.
I see.
So in this project, I think the idea was
sure. But you did use models of a unmanned ground vehicle, correct? Dynamic model of a UGV.
Yeah. We go back to this, right? We have this somewhere in here.
For what?
The model of the in.
Well, that's a two-dimensional model.
I see.
Yeah. In two parts. There. So you can see there's a little bit of our model. The x plus d cosine that's
right.
part of our model.
Right. It's more of a kinematic model, right?
Yeah.
I see.
Yeah. It was a 2D kinematic just because it was the problem. So we thought we could simplify it a little bit.
Yeah.
Sure.
So filtering the data real time was okay, but also there are processes in place, like for example, using some kind of chi-square test on your, the residual. So if your residual is bigger than some threshold, then you don't use that measurement. So
yeah, that's definitely what we would if we were to do this in the future or continue on, we would look into different methods of filtering.
I think it was like a day or two before we realized that our measurements were the problem, and so if we had a lot more time to like research how to best deal with that, we could have a much better result. But yeah, you'll be fine.
And the ROS learning part, I was like, getting emails.
That was rough.
You have
was really
students who know ROS, so if you need co-ops or jobs, ROS will come really handy. So I can forward that email to you guys if you're looking for some co-ops or. So learning ROS is worth it actually. So it's used a lot in industry right now. So.
Okay. Can you go to your R gain matrix?
Yeah.
So here you could try, like when one of your landmarks was having higher error, you could have used higher R value for that landmark, and you could have used lower value, so that would help you with tuning.
Yeah.
We didn't consider one landmark was actually having some kind of bias. So even I did the measurement and I saw that offset. So I think there was some kind of bias in that. So when real sensors tend to have some biases and stuff, so we might have to.
Yeah.
That's a whole other problem.
Any other questions? So all the judges, we are doing a sequence change. So instead of team 5 going next, so let's give a round of applause to these guys. Good job. So we're Krishna and Prashant and all the other judges. We are changing sequence a bit because one of the students says that he has a work at the job just pretty soon, so he wants to go next. So we'll call this team number 7. Okay, so grade it for team 7 now. Whatever the next people are coming is team 7. Is that okay, Krishna?
Sure, Rajni. There are only I see only 6 teams here, right?
I'll edit that right now. Okay.
Okay, 6 teams. So we are skipping one. Okay.
So.
So okay, so is it Ian, Rainer, Jamin?
No, this one is just let me.
Michael, Rechin, Iker, Santos.
They will come next, but I'm right now just putting their name. So these guys did not submit before, so now I'm just going in. Heather, right? Okay.
So this will be team 7, is it?
Yeah, it's team 7, final 2. So final 2, this one, right?
Yes.
So I'll create this team 7 thing. Let them present first, and so this is team 7. Just 1 second, guys. Yeah, this online and virtual, in person and virtual together is little tricky. Ah. So team 7 is this. Right now, just Heather,
Samir, and Mukhtar.
And Samir,
And Mukhtar.
and Mukhtar. Okay, I'll do the spell check later. But yeah, so I've created team 7 on your sheet. Okay.
Okay.
Okay, sounds good. So here you go, guys.
But we have completed only 4 teams so far, correct?
Yes, we have completed 4 teams. So 5th will come after this.
Thank you, Professor. Hi, everyone. Myself, Mukhtar Ahmed, and my teammate, Heather Jan and Samir Wala. Today, we are going to present a project on UAV landing on a moving vehicle. That's a ship in our case. Yeah. So, as I said earlier, we are trying to design a model to land a rotor on a moving boat. So we are using range measurements and EKF and controller LQR to make that happen. So the challenges that we are definitely facing is like we have to model the quadcopter and we have to estimate the position of the boat for the quadcopter using EKF and to design an LQR, and we are doing also like we are assuming that the ship has a, we are giving a dynamic model for also and doing EQF and LQR to for the quadrotor to choose the ship.
Thank you, Mukhtar. So our problem basically involves cooperative localization. The paper which we were using to solve this problem had literature pertaining to the fact that it said that there was vision-based systems that were being used by quadcopters to land it on moving platforms, but that posed the problems in rough conditions, where under rough weather conditions at sea or during nighttime where visibility is low. So what the paper proposes a solution that cooperative localization be used. That is, the quadrotor localizes itself with respect to landmarks around the ship or on the ship, and the ship in turn localizes itself with respect to the quadrotor. So these are the state space matrices we'll be using throughout this paper. We have state space of the quadrotor, that is all the 12 states. We have the states of the boat. So throughout this paper, we'll be using words like boat, ship, and vessel. They all mean the same thing. Just that sometimes we think a lot about process. So, yeah. Again, the states for the attitude controller, phi minus phi c, p, and so this matrix will be used as an input into the LQR controller, which will basically give us gains, and also the state space for the quad localization EKF and the ship localization EKF can be seen as shown. Next slide, please. So the figure on the right tells us the code flow, how our code works. Functions are being called from draw frame, and they go back into the draw frame again. So at first, from the top, we initialize our states, true and estimated, which and these states are inputted into the LQR controller, which gives us the gain k. So this controller is basically the trajectory controller. From that, we get a gain k, and that is again inputted into the EKF trajectory, into the differential flatness-based controller. Sorry, I've written LQR here, but it's actually differential flatness. It's basically the inverse mapping technique we're using for the controller. So from there, we get our force, our commanded roll, commanded pitch, and the yaw rate. On the left, we're getting a gain from the attitude LQR. You saw the state space that was being used as an input into it. And from there, we get a gain K. So F5C, theta C, RC, and gain K is inputted into the attitude controller, from where we get the torque to maneuver the quad rotor towards the ship, T5, T theta, T psi. Now that we've got our true states from the software IEC, we use those states and we basically add noise to them and render them as sensor values. Going towards the EKF block now. Predictions are based on the dynamic model of the quad rotor and the moving vessel. We have made separate equations for the dynamics of each. And in the measurement step, the location of the quad rotor is estimated using landmarks on the ship which are moving. So we're using three landmarks to estimate the position of the quad rotor. Alongside that, we're using sensor-based values from the IMU and from the gyro. After that, the location of the ship is estimated via measurement using a landmark that is placed on the quad rotor itself. After that, so now that we've updated the equations for the estimation of position for quad rotor and the ship, these variables now are inputted into the animation block, from where we get our animation for the quad rotor and the ship. And the loop continues on in this fashion. Next step, please. So the localization that is happening in our code is simultaneous. The quad rotor localizes itself with sensor values from the gyro, accelerometer, and the attitude sensor, and the range measurements from the landmarks that are placed on the ship. Simultaneously, the ship is localizing itself from the sensor values. We have the ship's angular speed. We're supposing that we have the ship's angular speed, which is omega in 2D. Also, we have the ship's speed sensor value, which is the linear speed, actually. The ship is localizing itself simultaneously also from range sensor value from a landmark that is placed on a quad rotor. So this is happening, all of this is happening simultaneously. Looking at our observability analysis, for all the loops in the draw frame, 600 frames, we're getting a full rank for the observability matrix, which is 7. The C matrix, which was used for observability, is a 3x7. Why 3? Because we are using 3 landmarks, so 3 values of range. And yeah, so we're getting a fully observable system, and we're using 3 landmarks to estimate the position of the quad rotor.
So in this case, when we were using 2 landmarks or one landmark, we were getting 5 rank 5. So it was not observable. So with 3 landmarks, we are getting full rank, so it's observable. So as explained by Heather earlier, that we are estimating the quad rotor's location with the help of 3 sensors and the landmarks on the ship. Then we, with the help of XSat, that is estimated location of the quad rotor, we are estimating the ship's location with the help of ship speed sensor and the ship's angular speed sensor. So that's the animation we are getting.
Oh, you have to. Animation is using estimated state.
Yes.
Is that correct?
Yes. So in this case, both our landmark, both our ship and coordinate are being estimated. These are the plots. So the orange one is the ship plot, and the blue one is the quad rotor plot. So our ship is in the north location we are ship is starting from 10 and ship is quadrotor is at 0. And east axis we are ship is starting from 0 and the quad is starting from -10. So the east axis and north axis are tracking well. But in PD and side equations plots there are error of 0.2 and 0.3. So we are assuming the PD is 0 and psi is 0 of ship. So these are the plots of the quadrotor, which is a rest to rest maneuver. So it is all the plots are starting from 0 and ending at 0. So
they were all estimated.
No, go. The PQR we are getting from the gyro, and phi and theta from different LQR we are assuming. So all are the estimated.
UVW estimated.
Yeah, UVW and estimated. So this is
general good idea would be like you also put true states so you can see how close they are.
Okay.
So this is the approach too we have done. Like earlier we were getting ship speed and ship's angular speed, but in this case we have assumed that there are 3 landmarks on the quadrotor as well. So ship is estimating its location with the help of landmarks from the quadrotor. So in total there are 6 landmarks. The 3 are on the quadrotor, 3 are on the ship. So quadrotor is estimating itself with the ship's landmark and ship is estimating itself with the quadrotor landmark. So no additional information of sensor in ship is there in this approach. So so there is the error while landing.
Turbulence. Yeah, we were getting some turbulence.
But after that, it's smooth.
So that turbulence is because of estimated states or because of wind?
Because of estimated
states.
Because in this case we are not getting ship's angular speed and linear speed.
Okay.
We were thinking of like saying that it's wind, but that would be like.
So in this case, we are assuming we are taking a dynamic model for the ship. We are assuming that the quadrotor dynamics and ship dynamics is same, and we are giving some trajectory using a differential flatness, and using controller we are making the ship to follow a circular path. And we are using that, we are estimating using EKF and we are estimating the ship position and feeding the estimated the attitude and velocity to the quadcopter, and using EKF we are trying the quadcopter to follow the ship. So you can see the animation, can you play? Yeah, so with the controller, we were trying to use the attitude PNP PD error only, but after some time, if there is some divergence, it would go like it was not really following. So we tried to use the velocity error as well. So we got a convenient result for this. So this is we are using.
Yeah, we didn't get enough time to work on this a lot. Yeah, but this was an alternative solution.
Yeah, so this is upload.
State convergence.
Can you go back to the plots?
These ones?
Just stay there.
Okay.
So is it estimated versus true or the commanded versus?
Yeah, this is the commanded and this is the estimated for the quadcopter. No, this is commanded for the ship. So this is command estimated for the quadcopter. Yeah, I think we can choose a better gain for good following. And we, given the time constraint, we didn't think we could add some more relevant slides other than just our results. So use us for that. And if you have any questions, yeah.
So you said you use the same dynamics for you use the same dynamics that you use for Quadcopter to the ship.
Yeah.
Is that so? Did you use what was the ship's dynamics? Is it just moving does it only have translation of move, or does it also?
Yeah, so you have Quadcopter's dynamic that we are using for ship. So what we did in this was by using differential flatness. We tried to we made the ship to follow a certain trajectory using LQR, and so we estimated that trajectory of ship for the quadcopter and quadcopter's position too. So we made that follow the path.
So,
yes, go for it, Krishna.
Yeah. So I had one question. I mean, this applies to previous teams also that are using quadcopter, correct? So I think the lift of the quadcopter is achieved by that particular slant it has as it is moving forward. So I was just wondering, in your dynamics, were you monitoring? Was there a set attitude pitch you would give as it's moving, and track that track that angle as it is during motion and also just before landing?
So were you tracking how your phi or theta commanded were looking while?
Yeah, we are getting it from.
So you're getting it, but did you see what kind of angles were demanded or commanded? So to move, you need to pitch a roll, right? To move sideways or so. So his question is, what were those angles looked like when you were landing?
Expected. Okay. Yeah.
Did you see or?
No, we did not.
We were just looking at the predicted values and how close it was getting to the ship. We weren't per se looking at.
Krishna, is that your question?
Yeah, absolutely. Yeah, I think you got it. Yeah. I guess the basic motion of the quadcopter requires a pitch forward, as to generate the lift or to generate the forward motion. I think pitch forward, right? So that aspect and the stability of that.
So what they have done is there are two parts of controller. One is the position controller. Position controller generates acceleration that this is how much you need to accelerate. And based on those accelerations, you compute how much pitch and roll the quadcopter should do. And then the attitude controller basically tracks those commands, right? So the fact that they did not crash seems like the phi and theta were okay. Otherwise, they would have been.
Yeah, they didn't explicitly monitor those variables, but they have. You need to have a particular pitch forward to generate the force, right? So I'm assuming if they're using the equations, then.
Okay. Any other questions?
Yeah. You had a case where you had 3 landmarks on the quadcopter.
Yes.
So did that make any difference? Because you can the distances are quite small between each landmark. So did that affect your estimation?
No, but earlier we were getting the ship's angular speed and linear velocity. In that case, the tracking was good. But in the second case, when we were estimating based on the landmarks on the quadrotor, the tracking is not good. Obviously, if we use 4 landmarks, the tracking gets better.
So the 3 landmarks on the quadrotor did make a difference. Like, what I'm trying to say is the 3 can be just 1 because the distance.
Yes. So yeah, it happens that when you increase the number of landmarks on the quadrotor, the estimation gets better.
It gets better.
Yeah, it gets better.
Yes. Similarly, when we estimate the quadrotor's location with respect to ship, if we use 4 landmarks on the ship, it gets better.
Yeah,
the quadrotor's estimation.
In case
How far were they?
Like 5 meters on the ship, and the quads is like 0.5 meter or 1 meter.
Okay. So but that means your quadrotor is quite bigger than.
No, opposite of that. Ship is 5 meter wide, and the quadrotor is.
Place your landmarks very close to each other. It becomes, if you look at real sensor data, it would be difficult to distinguish between both of them because of the noise association.
Yes.
So having 1 or 2 or 3 doesn't matter because all of them will be giving you the same values of data. How will that?
I was curious whether that improved your estimation.
Yeah, it was improving in our case.
I don't think they were far enough for that kind of thing.
Yeah, exactly.
If you are really far, like satellite kind of a distance, then maybe.
Yeah, that's.
And also the tracking was good when we use vertically opposite landmarks, not the adjacent landmarks.
you were using like 4 and 6 landmarks for 2 different cases. So, have you ever considered using relative equations of motion instead, where you could solve this problem with one just range sensor on a ship and
No, we are doing this in the inertial frame only. We are not estimating in the boat's frame or the ship's frame.
Yeah, then you wouldn't have estimated 6 different steps. It could have been just the relative pose
that
of.
would have been much easier.
Yeah, we tried to do that, but it was like we hadn't ever done that before, so we were like, it was hard to conceptualize.
Okay.
Not that hard, but like we started this on the fly, so we were like, okay, let's just go with this.
Somehow, I don't know, like this LQR tuning, we have always done tuning with zero noise, right? And estimated states are not ideal. So I was wondering if you need a different approach based on what covariance you are getting. That covariance basically affects your LQR gains. Then I think it would be, so basically you incorporate what is the accuracy of your states in your controller design, right?
Yeah.
That maybe as a research problem or something. Because you know how accurate your states are then, but you're using the same gain, same LQR gain to, even though the states are more jumpy, you're still using the same gain maybe. Maybe.
Yes.
Yes. We can apply some genetic algorithm into that EKF.
Okay. Any other questions? Okay, so this was team 7, folks, judges. Okay, don't put their grades to Michael's. But yeah, I think pretty good job. I'm happy you get definitely good points for observability analysis. The first robot you could have gone. This is a non-linear system, so you got away because you were only using the first row. But if you go further, then you will be in trouble. But anyways, good. Thank you.
Thank you.
So we are coming back to original sequence. Team number 5, right? You guys, team 5. Team 5, Michael and Ted and. So team 5. And we have Ted, who is online, right? Can you hear us, Ted? You there, buddy? Let's see. Hey, Ted, can you hear us?
Yeah, can you hear me?
Yeah, we can. So yeah,
Awesome.
your team is up and all set.
Awesome. I'm ready when they are.
So many PowerPoints. I need to close them. This is not, so let's close this one, right?
Yeah.
This is not ours. Let's close this. This is yours.
Yeah.
Okay, gentlemen.
Okay, so hello everyone. We are Michael, Ted, who is online, and I'm Iker. And we are going to present the LQR-based Quadcopter attitude controller. Okay, so I'm going to present the project scope and the attitude controller. Then Michael is going to present the motor characterization and system architecture. Then Ted is going to follow with the flight controller test and the controller code. And finally, Michael is going to finish presenting the challenges we faced and the system improvements and learnings. Okay, so our objectives with this project were to assemble a drone with the appropriate hardware, to build a drone testing bench where we can safely test the attitude controller without damaging the drone, to collect information about the physical characteristics of the drone to incorporate those into the final code, to find the right gains for the LQR controller, and to write a code so that the drone follows the commanded angles. Okay, so for the attitude controller, we used an LQR controller. We've seen this in so many assignments, so we must be familiar with this. The only thing is here is to find the moment of inertia of the drone to be able to compute the gains. And we can also play with the Q and R matrices to make the controller be more aggressive or more smooth. Okay, so for calculating the moments of inertia of the quadcopter, we assumed that there's a symmetry in the aircraft, that the mass is distributed, and that we can model the complex geometry of the quadcopter into a more simple one with simple geometries like parallelepipeds and cylinders. Okay, so as you can see here, this is the mass distribution and the dimensions of the quadcopter simplified. Most of the weight is located in the y-axis here because the battery is in here. So the y-axis is the one that's going to have the less moment of inertia. And the total weight of the quadcopter is 1.245 kilograms. Okay, with all that data, we calculated the moment of inertia of the quadcopter, but the actual moment of inertia that we put in the code was much more higher. This is because, as you are going to see in the next slides, the testing bench that we used has these metal rings incorporated, and the drone actually has to also move them in order to change its rotating angles. And also the mechanism is not perfect, so there's a little bit of friction there. So the effort that the drone has to put into changing its angular velocity is much more higher, and thus the final moments of inertia are these ones over here that are pretty much higher than the other ones we've seen.
So an important thing we had to do in this project was characterize both the motors and just the entire system. If you remember from like assignment 6 and all of our quad assignments, our attitude controller outputs torque, which in simulation is very convenient because you can just divide by force and get your angular rates. But in hardware, you have to actually send signals to motors and actually execute those commands. So we needed to first characterize how much thrust our motors create based on what signal we get them, so we can kind of inversely calculate what signals we need to send to generate which amount of thrust. So in the end, we were able to get this curve, so you can see we're ramping up our signal we're sending to the motor, and we have our expected versus actual thrust output. That's in grams. So each motor outputs about 700 grams at peak throttle. And then this is like a high-level block diagram of our system. So I'm kind of going left to right here. We have all of our sensors. So I guess the most important one is your IMU, which stands for Inertial Measurement Unit. This is the real-world sensor that gives you your phi, theta, psi, and PQR. Actually, it really just gives you PQR, and then you integrate it to find phi, theta, psi. And then we have a battery, a barometer, which I don't think is actually on here, and then a radio, so we can talk to it while it's in the air, because you can't obviously have a cord dangling from it. And then a microcontroller, which is a TC 4.0 for us. Motor controllers, which are these little dudes. They take our PWM signal from our microcontroller and turn it into like a pseudo three-phase AC that gets sent to the brushless motors. And then our radio transceiver is right here, which goes to your standard like RC remote. So as Iker mentioned, we had to come up with some test rigs so we could test this without sending quadcopters all over the place. So this is our one-axis test rig. So you see it's literally just a rod that goes through, I think this is our y-axis on our quadcopter. So we were just testing roll. And we could tune our gains and everything on here so that we were more confident when we actually went to fly it that it wouldn't go crazy. Go to the next slide. And then this is also the same rig we use for our motor characterization because we had a load cell sort of closed off in a box. And then we could measure the torque or the thrust created by each motor. And then Ted, if you want to talk about the 3-axis rig.
Yep. So we had to make obviously one for pitch and yaw. So that is this gimbal here. We made it out of aluminum to make it as light as possible. Unfortunately, one of the things we didn't take into account is that it was so light that a lot of high frequency vibrations passed through it, and it did disrupt the IMU a little bit. So here's the gimbal in action. You can see the quad rotor in the center. All the rods and everything are placed right at the center points, so that way you've got the actual roll angle. If you spin it in there, it'll spin freely. It won't try to gravitate back towards one position. Next. Okay, so the controller code is structured like this. You initialize all the variables, which means like you call all your libraries, you set all your defines, which are precompiled, and then you initialize all your values. In the setup function, you set up all the hardware. So if you're using an ADC, or if you're using, in our case, we were talking to a transceiver. So all that hardware has to be configured, which basically means you just set the registers up so that they perform a certain set of tasks. And then in our main code, that's where we get the measurements, and then we apply our control algorithm. So next. So you can see right here, this is the block diagram of the code algorithm structure. You can see we read in the commanded angle, we observe the actual angle and the angular rate, and then we apply our gain values to those, and that is what obviously results in the controller. One of the things we were looking at, and Michael will talk more about this later, is that the angular rate is constantly targeting 0. It would be really cool if we had it vary accordingly so that it would have better performance. Okay, next. Okay, so here's the code. Here's all the initializations. Next. Here's more initializations. You can see we actually used a matrix library so that we could program this as closely to the homework that we did as possible. So it's all done in matrix math. Okay, next. And then here's the setup. So this is configuring the motors, which have a certain pulse width that they're looking for that corresponds to thrust output. And then there's obviously a bunch of other things in here. We're sending some commands out. Next. Okay, this is more setup at the top, and then we've got functions, and these functions are used to talk to the transceiver. Next. Okay, here's the actual control algorithm code. So you can see we read in everything, we get the commands, then we go down and we get the measurements of the gyroscope and accelerometer so that we know our angle and angular rate. And then we apply our control algorithm. And then you can see there it says low pass filter. That's, well, quite literally a low pass filter that's smoothing out the signal. We went with a pretty light low pass filter because we didn't want to phase shift everything too much. Okay, next. And then this is writing all the commands to the motors and then capping everything. So like Dr. Sharma said, there are times where your motors can only output so much. So we're making sure that the program, even if it's trying to command more thrust, it doesn't actually send that to the motors because they'll get confused. Okay, next. And then this is just a serial print for diagnostics. Next. Okay, I'm going to let Michael talk about the challenges we faced.
All right, so a lot of the challenges we faced were just from the fact that we were using hardware. Like all the code Ted was going through, that's all in like Arduino C, which is like an embedded C or a flavor of C++. So when you're in hardware and you're on, embedded systems, you don't have infinite computational overhead like you do in Google Colab or whatever. So we ran into that, and also just some hardware compatibility issues. So spent a while trying to get our C communication to work. We originally wanted to use a NRF24L01, which is the chip that's on this guy. These are pretty cool little radios. They work on the 2.4 gigahertz band. They can actually transmit up to like 2 megabits per second, which is a decent amount for what it is at a range of a kilometer. And they just use the SPI bus on a microcontroller. But they're meant for like Arduinos, which usually run at 8 to 16 megahertz, whereas our TC 4.0s clocking at like 600 megahertz. So the SPI lines were at different frequencies. And we think this was causing the issue. Some people have gotten it to work, but we decided to just put our effort more towards the controller rather than getting radios to work. So we went with just a standard RC transmitter and receiver, and then we use pulse position modulation, which uses the interrupt pins on the microcontrollers to basically time between pulses into the signal from the RC receiver. And then IMU noise was obviously a big issue as well. Gyroscopes tend to drift pretty heavily, especially when you have cheap MEMS units like us. So we use what's called a complementary filter, which complements the gyroscope angular data with accelerometer data. This has the adverse effect that since accelerometer data can be pretty noisy, our IMU noise increased a lot, especially when the quadcopter was running and the vibrations from the motors were going through the frame and getting to the IMU. So we had another filter on top of that, which was the low-pass filter that Ted described. So down here you can see the blue line is your actual raw data, and then the orange line is our low-pass filtered data. Next slide. So we had to actually tune our filter as well. If you overtune or undertune a filter, they can do more harm than good. So on the left here is our final values, so you can see that although it's definitely smoother, it does eliminate a lot of the very noisy areas. On the right is a way over filtered value, so you can see it's very smooth, but it's actually shifted, and your filtered angle doesn't always actually represent the real angle that your vehicle is at. And then actually tuning the controller, the gains we initially calculated were pretty close. We had to do some tuning after the fact. You can see over here is a very underdamped controller. So this orange line is a beta angle we were telling it to target. So we went from 0 and then just stepped up to 15 degrees. So you can see our controller way overshoots, comes back down, does that for each commanded change. Whereas our final tuned controller, although there is still a lot of noise, it does reach the desired angles approximately. So here's basically that step change we told it to do, but in simulation. Might have to click the play button.
Yeah, I clicked that.
Cool.
The data looks so better. So
Yeah. Yeah, it's we definitely took for granted how nice it is to have the actual, phi theta psi values versus estimated and actual data. And then here's this isn't also tilted.
Oh yeah.
Let me rotate it real quick. Now I did it.
You want the Teams?
Yeah, actually, do you have a USB port? I have all the.
I don't think it has ports. Oh, it has?
I just want to go to that. I can just pull up the videos on there.
Oh, that's not it.
So you want.
Okay, there we go. Get it on here.
This is the 3-axis test data.
Yeah, so.
Okay.
Okay.
Yeah. So do one axis first.
Can Teams people see it? The video? Okay.
I could earlier, but I can't right now.
So I'm unable to see any video.
What about now?
Oh yes, now yes.
Okay.
So this is the test.
That's the normal one.
And then I'm going to go to the 3-axis tests.
This one 3-axis?
Yes.
To screen.
Oh, that's it? Oh, that's long.
We like the day.
And then we have 2 actual videos of us just taking it out of the rig and flying it. It did fly, but some of the issues may be because of pilot error.
Which one?
Do 1 and then 2.
So how do you know what it is doing? Like, did you plot this? Like what?
So since we were just able to transmit commands to it, we didn't see, we don't have the actual data for in flight.
Okay.
From the test on the setups, then we were able to record data.
Okay.
Those were the plots you saw. I was just trying to keep it in the air. So basically, we were just telling it, like, commanding
C and theta.
Yeah. So your pitch and your roll.
Manually transmitted that?
Yeah.
Like you said? Okay.
Yep. Yeah. So since it only has a attitude controller and no position controller, if there's any angular error, it'll start drifting. So you have to like constantly correct it and try to keep it in one spot.
Ready to go.
Got nothing.
Oh, it's still probably calibrating.
Like the fireworks.
That was no.
Anything else?
There's a couple, just like 1 or 2 slides though.
Or slides?
Yeah.
Okay.
More videos.
This one?
No.
Let's close this. This one? No. Let's close this. This one?
Yes. I'm going to go through the rest of them. So a couple learnings and maybe future improvements. Better filtering would definitely help it stay more stable. There's currently a low pass filter on it, but maybe like implementing a Kalman filter or Butterworth filter or something along those lines. Also, most off-the-shelf flight controllers nowadays, like a Pixhawk or anything similar, have multiple IMUs. So Pixhawks have 3 IMUs that they all feed into an EKF. So implementing something like that would definitely help to reduce the amount of noise we see. And then, you know, more LQR tuning. Maybe come up with a new way of calibrating the IMU so that it better estimates what its actual zero is. And then also maybe better mounting of different system hardware to remove some of the noise we were seeing from vibrations. If anyone has any questions, I'm more than happy to take them.
Questions?
Yes.
One question I have is the gimbal system. All that did you build as a part of this project from scratch, or was it existing setup that you had? It seems a lot for yeah.
Yeah, we had to build it from scratch. It took 2 days, going pretty much all day, but it was totally worth it.
Yeah, Ted,
yeah.
Ted, you're also doing this as like essentially your senior design as well. A little bit different objectives, but this is kind of tangential to.
Right.
was your individual contribution?
So Ted, you want to talk about what you did? We'll go.
I'm sorry, I didn't hear that question.
I got it. So Ted built the test setup and also assembled the quadcopter, and then him and I worked on most of the hardware implementation, the wiring, all the sensor stuff. Iker did a lot of the theory stuff, a lot of the estimating what our actual moments of inertia was, and then when it came to actually testing and tuning, we were all working on it together.
Yeah. Good amount of work for us. Questions?
The quadcopter, was it built out of a kit?
So yeah, kind of a kit. You don't buy the whole kit at once. There's like a lot of general parts. That frame is a kit, and then like the motor controllers are a kit, the motors are a kit, the propellers are a kit, but it's not just one giant kit. I will say one comment I'd like to make. It definitely makes me appreciate what control engineers and what they're doing with all these quadcopters nowadays. If you've seen like Jetson Arrow, they have like giant ones that you can get in and they're completely stable and they don't rock at all. It's really amazing. Michael was telling me they use a lot of visual AI to assist with their flight movement, and they have like redundant IMUs and there's sensor voting. Very impressive.
And all the controller implementation was on board, is it? Like what controller was it? Does it have a Raspberry Pi or?
So it's an Arduino Teensy 4.0. It's not actually made by Arduino. It's made by this other guy, and he basically piggybacks off the Arduino libraries, but he set them up for this controller. They're very fast. They're about 600 megahertz BGA processors, so they're really booking it. And one of the reasons we did that is because we were using a bunch of libraries, so a real embedded system is going to be written with arrays, no libraries or anything like that. It'll all be embedded C to get it as fast as possible. But in our scenario, to get around that, we basically just hardware accelerated everything so that we wouldn't have to worry about delays or anything coming up from serial prints and stuff like that.
Another major concern I'm having, because like you did so much, it's difficult to like piece out your senior design project and what was it that you did for this project, correct? Because if you just consider this, it's a fantastic project, according to my assessment. But
everything we did presentation is for this project. The hardware itself is also used in Ted's senior design.
So I think Krishna, that question senior design guys should ask. Like, I think for now everything is done for this, and then Ted goes to senior. When he presents senior design, then I will ask him, hey, how would you separate it out from your modern? Because I am his senior design guide as well, right? So he's in trouble. But I think so far, I think it's for this class. But when he goes to senior design, he'll have to show.
For this project, when we started with this project, we started from scratch, software and controller wise.
Software and controller wise, okay.
Yeah, none of that existed.
But the platform was built for the senior design.
The gimbal was actually built for this class. That gimbal would have never existed if Dr. Sharma hadn't motivated us to do that.
Okay. I hope you don't mind me asking these questions.
No,
not at all.
Okay. Any other questions? I think good job, guys. Thank you. So, team. So we have 3 teams left now. We'll kind of scramble.
Rajni, you have one question. So will you upload these videos because I have to step out in a few minutes?
Yeah, I will upload these and I will upload all the presentations as well.
So I can judge the other 2 teams, the few remaining teams.
No issues.
Thank you.
Is there an exam in this room after this?
I have no idea. Which should not be, right?
Well, there might be.
So I think there is always a gap. So we have officially till 3:30, and then there is always a gap between next exam, like a 1 hour gap or so. So we should.
Until 3, I realize.
So yeah, we are here till 3:30 for sure. So we are here. So this is team 6 now. Like another landing thing.
Different.
Okay. No time starts now.
All right. So on behalf of Group 6, I'd like to welcome you guys today for our presentation on autonomous landing of a quadcopter on a moving boat with wind and wave effects. So without further ado, I'd like to jump into our table of contents. We'd just like to deliver our background and motivation of our work. And also, I will touch on details of our contribution and what separates our work from the previous works introduced in different literature over a decade. And as our third point, we would like to validate our work by analyzing the test results from some of our simulations. And then we would like to close our presentation with providing you with some future work and maybe rooms for improvements upon our work. So one of the rules of the air that stuck out to me was every takeoff is optional, but every landing is mandatory. So you'll take off, but you have to land. So a manned aerial vehicle, or UAV in short, have received wide attention due to its capability and potential for diverse applications in military and civil fields. In fact, the British Royal Navy have actually showcased automatic landing control on a moving boat based on a visual approach. One of the engineers who participated in the project discussed that landing on a moving boat with wave effect was the most hazardous part. And then since the faulty landing is very costly and complex, that was the reason that kept the adoption of UAV in most of the naval operations. So in our work, in our project, we would like to utilize the range-based autonomous landing procedures of a quadcopter on a moving boat. That separates our work from the vision-based UAV, since range-based, we're using fixed beacons on a boat to estimate the states of the quadcopter, allowing us to expanding the operation range to inclement weather conditions and night times. We also we have added wind and wave disturbance to mimic the real world application, and also for safe and risk avoiding a landing, we have implemented 2 different landing phases, approach and descent. We'll go into details as we discuss our contribution. We have used a reference paper from a university called UNIST from South Korea. And
so for our EKF, we used 2 sensors. We used similar to homework 6 or 7. We used the gyro and accelerometer with noise added to them to kind of simulate real world noise. And we assumed phi and theta were estimated as separate EKF that was not simulated in this simulation. The prediction model for quad rotor was similar to, or the same as homework 7. We predicted the position, velocity, and psi. We assumed that we did it in the quad rotor and boat in the inertial frame instead of the body frame. We didn't reference just, yeah, we just did it in the inertial frame. And we measured range from each of the landmarks and bearing from each of the landmarks. And then the 4 landmarks are placed on each vertice of the boat, and we assumed we knew which landmark was at which position, and we knew where the landmarks were at all times. And then we also modeled wind and wave disturbance. One thing we did assume is that the ship was not under heave, surge, or did not translate an X, Y, Z frame. It only moved up and down and rotated left and right. And for wind modeled, we only assumed wind was going to affect the thrust of the propellers. We did not account for any drag or aerodynamic effects on the quadcopter body itself. So the equation up top, these were each of our wave motions of the boat with PD, psi, and theta, or P theta, or phi and theta. And then this equation here is the force of the wind affecting each propeller over a sine angle. And then putting it all together, let's create our ship equations of motion. As you can see there, the ship was assumed to be moving at a constant velocity and a constant angle, or psi.
So once the state of the quadcopter was estimated using 4 beacons installed on four vertices of the boat, we can now we proceeded to calculate or do trajectory planning using a differential flatness. There were we have used 2 different phases for landing, as I discussed earlier. The first one is approach phase, where the quadcopter will align with the position of the boat 10 meters behind while descending to the altitude of 10 meters. And then the second one was after the descent phase, after the quadcopter is aligned with the position of the boat within certain range, it will start slowly descending with a fixed descent rate. For now, so those two, so the trajectory planning using differential equation, differential flatness was used to create reference trajectory and the reference input of the quadcopter, which was then controlled using LQR-based control like we did in assignment 6. So our control inputs were the position and the velocity of the quadcopter. We have actually set psi to follow 0 instead of psi of the boat to minimize the disturbance caused by the psi of the boat. So as I discussed, to explain the approach phase, a quadcopter will start from a distance, and it will start descending down to the altitude of 10 meters above the boat. Since the boat is going up and down due to the wave, it will maintain the 10 meters above the boat altitude, but also line up in X and Y plane. So once the altitude is met 10 meters above the boat, it will then slowly move to the landing zone. So it will slowly minimize the error between PN and PE between ship and the quadcopter. And then our second landing phase, which is descent phase, is initiated when the north position and the east position between boat and the quadcopter are within 1 meters. And it will once that condition is met, our quadcopter will start descending with a rate of 1 meters per second. 1 meters per second is a good rate of descent, so it will prevent the quadcopter to crash down or move too slowly. One protocol that we added is that since the boat's pitch and roll are constantly changing due to the wave, we have implemented a mechanism where the roll and the pitch of the boat is above 5 degrees. The quadcopter will maintain its current altitude, and then it will wait for the boat's motion to settle down, and then it will start descending again.
Then we'll talk about the testing of our model. The first one is the shape moving to the west direction, and you can see obviously it shows the 2 phase about our controlling. The first one is to approach and sail way behind the boat, and then next it will landing on the ship like slowly. We also draw the several figures about the states and our arrows about other parameters. And we also like find the two time domains about this different phase automatically. And for the straight line, it shows the approach process, and the dash line shows the landing process. And from the PD figure, we can see that it finally landed on the ship. And for the other arrows, you can see they are nearly remain at 0, except the W, because the W, the speed of this vibration is caused by the shape that here is moving up and down by the wave. So it will show the sine function like that. And we change the angle and move the ship to the northwest direction, and it's also finally landing on the boat slowly.
Those three.
Those are just leftover animations from something else that break when I remove them.
There are some coordinate frames.
Yeah, they're coordinate frames that move when the quadcopter moves. When I comment them out, the whole simulation breaks, so they stay.
And also we did a lot of several plots.
And then one thing you notice here, the air covariance seems to grow after the quadcopter lands. That is us due to us hard coding the quadcopter's position to land on the boat in the animation. So it's not actually growing, it's just because we fixed the variables. So that's where you see those covariance grows.
So in order to make sure that to mark the moment of touchdown, we have created a flag when the PD error is below a certain number. We have considered the quadcopter that it has touchdown, and then we have overwritten the states of the quadcopter to follow those of the ship.
Then we'll for the future work, we may develop the adaptive controller for the wind disturbances, and also we can add more quadcopters on the several boats or landing on the one boat, and we can do analyze for the stability of our model. Thank you all. And is there any questions?
So all our controller was always using estimated states.
Yes.
Yes.
Questions? Good work. This is good.
So this is Prashant. I have a quick question. Maybe I missed it at some point. You said in the beginning that you validated your results with something. Could you talk a little bit more, or maybe go back to the slide which I may have missed?
By saying that we have validated our approach through the tests. So I meant these error plots. So we have verified that our approach of having two different landing phases have successfully landed the quadcopter. If you look at the PD plot, you can see that as we intended, it will first descend to 10 meters above the boat.
So I think the confusion is Prashant, by validation, do you understand by some kind of hardware or something, or?
Yeah. So if
okay.
So yeah, validation using simulations is what they were saying.
Yes.
So their algorithm being validated using
yes.
simulation.
Okay. Okay. Thanks.
Any other questions? Okay, we'll let you guys off the hook. Thank you.
Thank you.
So we have team 8 now, Shrikant, and I created Prashant and all the judges. I created team 8 there, Shrikant, Anuraga, and who else is there? Satyam. Satya. Let me get your presentation. It was not there when I checked. So this is second last. After that, we have one more team and we'll call it a day. Who submitted it? Right. It just says, I don't see any. So let's see.
The
Anuraga,
previous team was Ian, right? Ian and Tim?
Yeah.
Okay.
Yep. Yeah, I don't see any presentation yet. What is their team's name? Like, what was that? So, Surender. Okay, so that will be then 9 teams. So we have total 9 teams. Download. So why don't you guys come, Surender, and while these guys are submitting. Okay. Oh, he went to restroom. Okay, good. Good timing. So the team 8 and then team 9 will be team 9. So Surender, and who's your partner? Abhishek. So that is team 9. So are you submitting? Sorry guys for the. So let's see, Anurag. Who is submitting? Anuraga, are you submitting? You can email me also at this point of time if that's easier. Maybe next time I should put some points for this. Hey guys, we have a couple more pizza boxes. So if you want to go for evening snacks, please go for it. So yeah, let's. Judges, we are going team 9 first, which is Surender and Abhishek. Okay, Prashant and everybody else. Surender and Abhishek, team 9 is going now. So.
Okay.
Is this 310, right? Okay. Yes.
So hello everyone. I'm Surendra and this is my friend Abhishek. We are here to present our project localization of ground robot using extended Kalman filter. And this kind of agenda for presentation, we'll be talking about the problem statement first, and then we'll be going through some basics of localization and EKF. Then we'll be talking about the process flow and the setup and state space, and then we'll be talking about some of the results. So this is the problem statement. The main goal of the project is to localize a robot using EKF and decawave ultra-wideband sensors. And so when we think of a robot, the first thing that comes to our mind is autonomy. So for a robot to be autonomous, it has to be aware of its location. That's where the localization comes in. So yeah, like as I said earlier, so the robot finds out its estimated position. That's the localization. In our case, we'll be given the landmark positions in the map, and robot gets the sensor readings from it, and we'll be using it for localization. Yeah. So, like as I said earlier, so we'll be having that landmark position and the sensor data, and we'll be finding out the estimated position. So before going to the extend Kalman filter, first we'll talk about the Kalman filter first. The Kalman filter finds the optimal state estimate by using the measurement noise and the process noise. So, but one of the main drawbacks of Kalman filter is it cannot be used for nonlinear systems. So that's where extended Kalman filter comes in. So in our case, all our three states which we'll be seeing next are nonlinear because of the presence of cos and sine.
Okay, this is the flowchart of general process flow of the Kalman filter. To start with, we are initializing our initial parameters such as velocity, angular speed, and the covariance matrix. And the next step is the prediction of state values and the covariance matrix. So by using the prediction equations. So once we get the range measurements and values from the sensor. So in our case, we are using the Deca wave sensor. So the data will be associated with the predicted values before, and we'll be updating the state estimates, and we'll be updating the error covariance. So for our case, for getting the range measurements, we use this test setup, and we had 3 landmarks in different locations, and these are all the coordinates. And we also have one Deca wave mounted on the robot, which we referred as tag, and which is responsible for sending and receiving the radio signals for the range measurements. And we also got the true value through the motion capture using the camera. So this is our state space. So the state space is generally for the mobile robot, and consider this as a robot's environment. So we do have 3 states and 2 control inputs. So Pn is the
equal to sign missing, right?
Sorry, sir.
X dot. Is that multiplied by that matrix, or
yeah, multiplied by that matrix?
Not a it's not a good multiplication for matrix work.
So
Are you missing some equal to here, or it's multiplication? It should be P and dot. I think it's a typo, but
yeah,
it's not a. Yeah, that's not a.
So here the Pn is. So we got 3 states here: Pn, P, and Psi, and this is how our state space looks like. So since this is in nonlinear form, so we need to linearize it for filtering. So these are all initial parameters. So P EKF is our error covariance matrix, and these are all initial states. So we took our first measurement state as our initial states. So, and these are the sampling time, and velocity and angular speed is constant for the whole process. So this is the algorithm that we use for extended Kalman filter. So as I said before, we are initializing our parameters. So once it got initialized, we are moving on to predicting stage. So we'll be predicting the states since we till we get the sensor measurement. So in our case, we are getting the sensor value once after every 10 prediction steps. So we'll be calculating the Jacobian by linearizing the function with respect to all other states. In the same way, we'll be predicting our error covariance matrix. And once we get the update, we'll be predicting the Jacobian matrix for our measurement equation. So once we got the C, and we'll be calculating our Kalman gain, and with help of that Kalman gain, in the same way, we'll be updating our states and covariance. So these are the results that we got The first plot defines the shows the X portion with respect to time, and the second plot
which
shows.
one is which? Like,
So
is
the orange one is the true state estimates, the true state values, and the blue one is the estimated values. And that is for Y, and this is between X and Y position.
So was there any updates happening here, or?
It's happening.
Okay.
So these are the error plots that we got. So these are the 3 sigma boundaries, and somewhat we are getting the error going out of the boundary, and in both the cases. So this is how our robot moves.
What about to heading errors? Did you plot heading errors?
We have not plotted.
Any specific reason?
No, we didn't do that. So we gave the same initial condition for both true values and the estimated values.
Seems like there is no correction happening there. See what I'm saying? Like the measurement should pull it towards the. It seems like it's going on its own prediction. Like, are you sure your estimate, like EKF was being measurements were updated?
Yeah, for every loop I was shaking it processor.
Because you see what I'm saying? Like it should be pulled. Like it seems like it has its own velocity. It should be pulled.
Because the trajectory on each loop would be different if there was some kind of problem that happened. Otherwise, it looks like it's only running.
It just looks like it's just running on a prediction step. It's no update happening here. We can discuss.
Okay. So, and the main application of this extended Kalman filter is localization, and it is the key for all the autonomous vehicles that we have right now. So for the localization technique has to be able to measure the uncertainty in locating the location estimate. So this localization plays a vital role in this EKF plays a vital role in localization. Yeah. Thanks.
Thank you. Questions? So yeah, I think it seems like there was no update happening. So it's a big the heading plots. So why don't you revise your slides and then submit?
Yeah.
Put some heading plots and check your. Did you put link of the code?
Yeah.
Okay. Yeah, it seems like strange, but otherwise it should pull it towards.
Sorry?
You did it using ROS?
No, we have not implemented ROS on this, so it's just Python.
Also, it would be useful to put legends on all your plots so that we know what we're looking at.
Like which one is estimated, which one is true.
Sure,
so those kind of things should be there.
I'll do that.
Any other questions? Okay, thank you, gentlemen. Guys, the last team, final. Did you submit now?
Yeah, she submitted on the wrong one.
Final assignments.
What?
T-Max. Okay, we have the final presentation. So this is team number 8. for judges. Team number 8.
Hello. I hope you're not too exhausted for us. So I'm Satya, this is Shrikant, and that's Anuraga. Our project is implementation of EKF SLAM for ground robots using UWB sensors. To go through the contents, we'd first be going through the problem statements, the process flow, what's localization, SLAM, our algorithms, the results that we obtained from the project, our shortcomings, and the acknowledgements. So with this project, we aimed at estimating and localizing the ground robot and the deca waves. We did this by using the extended Kalman filter to perform SLAM. So the process flow of SLAM would be, we would derive the inputs through odometry and IMU, which is used to predict our states. And then we obtain the raw sensory data from the sensors with respect to the landmarks, which is then used to make a measurement prediction, which is then later used to make an update on the state. So we know what localization is. We are working on an unknown environment. So
localization is known.
No. Yeah, it's a known environment. No.
So, as we already know, localization happens in a known environment of that is, we already know the positions of the landmark, and using that, we estimate the robot's pose. In the current problem we have, as we know, we just use the 3-state system for this. That's X, Y, and psi. That is the position in X, Y, and the heading angle will be our states. And our control inputs would be the input linear velocity and the turn rate. So this is the motion model that it follows, the robot follows. So mathematically, SLAM and localization are kind of similar, but the only difference is the number of states in SLAM would be a little more, because we would be estimating our landmark states along with the robot pose. That is, we assume that we are in an unknown environment and we don't really know anything about the landmarks. So the state space in this case would look like, along with the robot pose X, Y, and psi, we would have to estimate the landmark positions X and Y. So if we have, say, n landmarks, the total state space size would be 3 plus 3 robot states plus 2 into n being the number of landmarks. And the control inputs would remain the same. So as we know, the EKF has basically 2 steps, the prediction and the measurement update. So we just use the same motion model, the V sin psi, V cos psi, and omega to propagate our motion model. And then we take the 3 range sensor data to update our states and the covariance. So the only difference here is our states would kind of remain the same, but the covariance matrix would keep changing with the measurement update.
So when we do the measurement update using 3 locations, 3 landmarks, we initially assume that we initialize the landmark location as an initial guess, give it a guess, saying we think this is where the landmark is. So for that guess, we use the true location of the landmark given to us, and then we performed our EKF and got these plots. So the reason we see a little difference between the true estimated state and the true state is because the time steps we used did not accurately match the time step used in the true states, and the motion model could not actually capture what the motion capture predicted. Motion capture gave the data as, and then there are also disturbance between how we make the measurement update. So we assume to make measurement update at every 10 steps, but in actuality, the update was happening randomly. That is, it was happening at 9 steps at once, and then 11 steps at the other time, and then
the difference was variable, so that we could not capture when to exactly make the update based on the given data. So that's why we see a difference and which gets propagated. And the reason we are getting different size because the input, the true size data was given to us in degrees, and we were calculating our trajectory in radians. So we could not wrap the radians into -90 and 90 bounds in Python.
I think
So the reason the true trajectory for the size is because it's bounded between that and ours is radians free flowing.
So is this a SLAM result or is
SLAM result?
This is a SLAM.
SLAM.
Where are the estimates of? It's kind of a cheating. Like your landmarks are stationary objects, right?
Yeah.
And you are starting them at true position. You are saying that their x dot equals to 0.
Yeah.
And basically, it's a localization problem.
So, but in our state space equation, we included the landmarks, and because our covariance matrix changes, the landmarks.
Still, you're saying x dot is 0. So prediction model always says this landmark is not moving. You know the true position at the starting t equals to 0. So saying that you're navigating in unknown environment and all those conditions are kind of.
So the right way to do that would be take the relative distance between the landmark and
the initialization process. You use the range measurement and then whatever just initialize them randomly. That would have been a true test of localization. It seems like it's just a localization problem.
Okay, so
because of the dynamics, your landmarks are not moving, right? So.
Yes, so that's also the reason why we get an almost zero error in the covariance plots, error covariance plots. So our error covariance for x and y stay within the bound most of the time because it becomes a good localization problem. And then this is what our animation result gave us.
I could have idea would have start randomly. This whole area randomly pick 3 positions and let them converge.
Yeah, so that's the reason why the landmarks are not moving for us. So if we initialize it randomly, our
but the
trajectory
updates will put it there, right?
So we tried doing that, but it was working for one, and then when we increased the number of landmarks, even our trajectory for our robot was getting messed up. So even for that reason, we had to take our R values closer to 1 than less than 1.
But you don't have to match the result, right? That's the.
Yeah.
So you wanted to get an answer rather than showing what the is anyways, yeah.
So that's about it. So I'll be open about my shortcomings. The SLAM was not well defined. We did not define our projects clearly. We wanted to implement this in RAWs, but we wanted to create our own node, which was somehow not happening. We were getting version mismatches between publishers and subscribers to the turtle bot. So we wasted a lot of time instead of testing out our EKF than doing the RAWs. And we would like to thank Rohit and Ishan for all their help. Rohit for providing the data, and Ishan for help initializing us and how to do the project, and Dr. Sharma for lending us the equipment.
So yeah. Questions for the final team, Team X? Questions? It's like too much pizza.
Your estimates look way too small.
Yeah, so our faith in the measurements were not good. So when we tried to prediction, the prediction we put the error on error weight on the prediction less and more.
We stop the recording. Yeah, if no questions, I will like to thank all the judges, Rohit, Ishan, Dr. Khare, Dr. Kayappa, Did I miss anybody?
Is it there on the team with
No.
Samir and Heather?
They did it actually.
Oh, they
They
did it?
switched.
Okay.
Yeah, they did when you were, I think. So they were team 7, but they came before Michael.
I see. Okay.
So they did. They have done, I think. But yeah, thanks Prashant for. So I can upload all the presentations, then you can look at the presentation before you finally grade them. And okay. And yeah, it was a fun semester. Thank you. A little bit difficult with maths and all, but I think still better than totally virtual semester. And yeah, it was hard. I will say the problems and things were time consuming, but I think you hopefully you will remember the stuff. And yeah, keep in touch via LinkedIn, via Gmail or whatever email. I can follow what you guys are doing later on after taking controls, aerospace controls at UC. So yeah, I'll be grading up. Don't forget the ONR evaluations. That's important for us. We get money that we can use for TAs and all that stuff. So it's good for. And also don't forget to do the UC evaluations. Thank you. Feedback. Did you like Python or not? Or it was a bad experience or a good experience, whatever it was. But yeah, thank you very much. And safely enjoy your holidays. And I'll hope to see you next year. Some of you at least. Okay. And make some good engines there. Okay. Thank you, everyone. Thanks, Prashant.